In this lesson, we'll be taking a look at another conic section. This time will be circles. So circles are very, very closely related to ellipses. That's why they are on this same set of slides here. The only difference with a circle is the vertices and co-vertices are the same distance from the center. So instead of getting an oblong sort of shape, we get a perfect circle. So how do we go from an ellipse to a circle? That is a concept called eccentricity, which is how stretched or round an ellipse is. So the bigger the eccentricity is, the more oblong, the more elliptical the shape is, and the lower that value is, the closer it is to a circle. So eccentricity is always a value between 0 and 1. I think it might be strictly less than 1. So if the eccentricity is 0, it is a circle. If it's close to 1, it is a very, very, very stretched ellipse. So how do we find eccentricity? Well, it's a really easy calculation. It is C over A. C is the value that we were finding last time. That's the distance from the center to the focus, and A is the distance from the center to the vertex of the ellipse. So if those two are the same value, C equals A, then we will get 1, and that is a very, 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 very stretched out ellipse. When the focus gets closer and closer to the center, that makes the C value close to 0, and that gives us more of a perfect circle. So again, we find the C value from taking a squared minus b squared if we had those in the ellipse. So we would be able to evaluate it. Right here, I've just given us an example. C is 8, A is 10, so that has an eccentricity of 8 over 10, or 4/5. So for this example right here, we have x minus 3 quantity squared over 100 plus y plus 3 squared over 36, and we're asked to find the eccentricity of this ellipse. So all circles are ellipses, but not all ellipses are circles. That's the same thing for like rectangles and squares. So it's best to call it an ellipse until you know for sure it's a circle. So for this ellipse, we're asked to find the eccentricity. So the steps that we need to take are to find A, to find B, to calculate C, and then write that fraction. So if you want to take a moment to pause the video and go through finding A and B and then calculate C to get your fraction, do that at this time. Okay, so if we look at the notes from the ellipses, A is the number under X or Y, whatever one's bigger is A. So 100, that's bigger, which means A is the square root of that, so A is 10. B is the other denominator, square rooted, so 36, that gives us 6. And then for C squared, it is A squared, which was 100, minus B squared, which was 36, which gives us 64. So actually, I think those are the answers to this problem that was already set up. So C should be 8. And the eccentricity of this is 4/5. Okay, so that is very, very basic on eccentricity. It's a really minor thing to do. We're more focused on graphing the circles and what the equations look like. Speaking of, here is the process of taking a ellipse equation and getting to the circle equation. It's a very easy process. So what happens when we have an ellipse that has the same distance from center to vertex and center to co-vertex? So when A and B are the same value, we can rewrite the equation as x quantity squared over a squared and the y quantity squared over a squared as well. So they are both over a squared. Then we can multiply both sides by a squared, and we get this equation. They don't write it or present it to us like that because with a circle we are used to the quantity r, the radius. That's in basically every circle formula we know. So they go ahead and switch that a to an r, just so we're aware that, hey, this is a circle since it's got an r squared in it. But it's the same equation that we just saw. So that's our equation. This is the simplest of the conic equations. It is the same sort of general setup with the x minus h, the y minus k. Everybody's squared, and it's the old circle formula we hopefully learned as part of the trigonometry, where it was x squared plus y squared equals r squared. This is the same formula as that. The only difference is the circle can now be centered anywhere. Those trig circles were generally centered at the origin. This has the ability to move around the coordinate plane. Okay, so super easy sort of setup for the equation. So they throw us a very difficult first example here, or as difficult as they can get. The problem is listed in sort of standard form, and we are asked to get it into this vertex sort of form here with the x minus h quantity squared, so on and so forth. So we need to do the completing the square process on this problem, as we've done for one of the problems in each of the sections. So completing the square, it works to move any of these standard equations into the vertex equation for any of the conics. So if you remember that process, great. If not, what you should do is get the constant to the other side, isolate your x's and y's from each other, factor out anything common, and then do the completing the square process, which is the b term divided by 2 and then square that. Added in on the left side, also added in on the right side. So if you want to go through that process, take a moment, pause the video, do so now. Okay, so our first step is to subtract the 12 to the other side. And we don't really do too much there. So I'm going to go ahead and rearrange these as well, just so we're not wasting a bunch of space here with very little work. All right, plus 10y, I guess we'll move that to 12, a little bit closer there, equals negative 12. Okay, so we have this. Now, if we look at these x and y sets, there's no leading coefficient, which is good news. We don't have to factor anything out. There's really nothing that we could factor out. So we can go ahead and start the completing the square work. So for the x, the b term is 12. So we'll take that divided in half and then square it. So 12 over 2, 6 squared, 36. And then remember, we have to immediately subtract 36 as well. I'm going to do it a little bit different here just to show you another look. Instead of doing that and then moving it to the other side in a later step, what we can do is add 36 there and add 36 to the right side of the equation. So instead of worrying about subtracting and moving things over, we can just add it to both sides of the equation and it still keeps us balanced. Same idea for the y. We have y squared plus 10y. The middle term here, the b term, is 10. So 10 over 2 is 5, squared is 25. So we will add 25 to that side as well. So we have 36 and 25 makes 61, 61 minus 12, 49. And that's good. So that's a perfect square. That's good. It doesn't have to be a perfect square. We saw that in the ellipses. They don't always have to be perfect squares. 49 is, so that's good for us, and then we move on. So now we need to factor these x and y's to be the difference, or rather a perfect trinomial. So we have the x. We always use the first sign right there, so that's a minus. And then whatever our b over 2 was, which was 6. So x minus 6 quantity squared plus y, that is a plus sign, so plus, and then 10 over 2 was 5, quantity squared equals 49. And that is the vertex form of the equation, as I call it. So now we are ready to graph. That's the last component to this, to all of them really, is to graph. And we just need to be aware that everything is a square. So this quantity for x and y, easy to remember their squares because they have squares written on them. It doesn't really impact what we're about to do, but we need to remember that that is a square. 49 is the radius squared. So when we go to graph these, it's not going to have a radius of 49. That would be an absolutely massive circle, and that's not what we're after here. So radius squared is 49, so radius is 7. Very important to remember to take that square root for your radius part. Okay, so to graph this, we're going to plot the x and y for the or the center of the circle. So we are at 6, -5. So 1, 2, 3, 4, 5. There we go. And then we're just going to do the same idea that we had with the ellipse. We're going to go up, down, left, and right. Instead of doing 2 different numbers, we're just going to go 7 all the way around. So 7 up, down, left, and right. So 7 left will put us there. 7 right, 1, 2, 3, 4, 5, 6, 7. 7 above, 5, 6, 7. And 7 below, 1, 2, 3, 4, 5, 6, 7. Ran out of graph. Should be down there. Okay, so again, these should look rounded. It should not be a square. Don't just play connect the dots. We do want it to look somewhat like a circle, but circles are a little bit harder to draw, especially when you've just got these 4 points. So it'll probably end up looking a little boxy. That's okay. I sort of missed the whole dot there. So sometimes it works better to go in between them. Sometimes it works better just to try to do the whole thing. Or if you're doing it on a device like I've got, you can probably just make one and move it on top of it. Sounds pretty close. I can change the size a little bit. I don't think it was a perfect circle to start. Anyway, you get the idea. So the graph should be a good approximation, and it should look rounded as much as you can. Try not to make it a square. Okay, so that's really it for this one. There are some other setups they can give us. They can obviously give us a setup where they give us the vertex form, and then that's super easy. The center is just the opposite of what's inside, so like x minus 6, that means positive 6 on the x. That's super straightforward. We've been doing that with all of the other pieces of the conic section. They can also tell us that there's a circle centered at 2, 3 with a radius of 4. That is basically giving us the same as the vertex equation. You just plug everything back in, and it's super easy to graph from that. So there's only one example for this. It's a very quick section. Again, circles are ellipses that are the same distance from the center to the vertex as the covertex. So it's a lot of the same skills that we saw in the previous set of notes on ellipses. So that'll do it for today. There is one more conic section that we will cover in the next video, which will be hyperbolas.